Thank you very much for the invitation here. I'm very happy to be in Bangalore again. My lectures, I think, will differ from what I seen so far here and the last week, what I've seen on YouTube. Yeah, that they will be a bit more particle physics-y than what is the rest of the lectures. Maybe more standard. Yeah, but I hope I will also give you some interesting details here. So my goal is to connect high energy physics to low energy observables, to low energy precision observables, yeah, and show you how to extract constraints on new physics beyond the standard model, yeah, from like host of different observables. So I will start today. Today will be very light lecture, like general introduction and overview of SMEFT. So SMEFT will be like a central point, yeah, of course, explain what I mean by that. It will be a central point of this lectures, yeah, and with the starting point, and then I will be trying to show here how different kinds of observables that refer to low energy. Well, low energy is defined in a very defined in a very different ways, but let's say low energy is well below the current energy frontier. Like how these observables allow you to constrain operators in SMEFT, and with this, how they constrain new physics beyond the standard. So tomorrow, in the second lecture, I'll tell you about electroweak precision observables. Very classic topic, yeah, but this will be with this emphasis, yeah, on how we can constrain a host of SMEFT operators using those observables. So electroweak precision observables, in a sense, like Z boson and W boson decays. Then I didn't find a good title for that, but low energy probes of very high scales. So there is several observables that at low energies, yeah, that probe very high scales that are well above the current energy frontier. Like, for example, proton decay is like extreme example, but there is more of that. Yeah, there is electric dipole moments, G-2, and then a few others that allow you to probe really very high scales with precision experiments at low energy. That will be tomorrow. The day after tomorrow, I will talk about two topics that I've been working on a little bit in the past years. How you constrain SMEFT operators with meson decays and with nuclear beta decay. Yeah, so my nuclear physics, yeah, this will be like nuclear physics, yeah, for dummies. Yeah, that is I'm at the user end, but I'm just trying to understand the data and use this data to obtain some new constraints, yeah, that you cannot obtain otherwise. And then if there is time, if there is no slip up in time, yeah, the last day, I will also tell you about the constraint on new physics you can get from neutrino scattering, like for example, coherent scattering, and from neutrino oscillations. So that's the plan. And let me just start with a general introduction. So when I was attending schools as a student, yeah, the world was much simpler than it was today. Yeah, so we had we knew exactly, yeah, how the world how the like fundamental physics is organized. Yeah, so there was a string theory at the high scales. Then that was above the string scale, which was of the order of Planck scale, and that was the theory of everything. Then below we had grand unified theories. We knew exactly, yeah, where the scale of grand unified theories is. That was 16 GeV. We had then there was a big desert. There was MSSM that extends up to scales of order 100 GeV. and then there was a standard model. Yeah, so we had this top-up approach. Yeah, there was a dream of the fundamental theory. There was some small bemol here that there was maybe more than one string theory, so we didn't know which one. But yeah, everything was very, very neatly organized. Yeah. So of course this worldview has crumbled. So the paradigm has completely changed during this maybe 25 years. I've been doing physics, and now like everything was fundamental in the old days. Now everything is effective. So there is now we are in the era of effective theory. So the worldview is completely different. So now we have a at the high scale, we don't know what it is. Okay, so it's some sort of monsters, dragons, and we don't know where the scale of this new physics is. Then below this scale, we have a realm of so-called SMEF, standard model effective theory, that goes down to 100 GeV. Below, this has different names, yeah. Wet, left. These are the names more often used in the literature. I call it WEFT, weak effective field theory, that goes down to scale of something like 2 GeV, further 2 GeV. Then we have Cara perturbation theory, and there is no more space, yeah. But yeah, and we go to QED. And if you go even below, you have a Euler-Heisenberg effective theory where the degree of freedom is light. Only degree of freedom is light. So this is description of the world right now. So we don't know what is the fundamental theory. At each scale, we use the effective theory, yeah, with the degrees of freedom that are available. Yeah. So at the here we of course don't know what the degrees of freedom are. Here we have the degrees of freedom of the standard model. Here we have degrees of freedom of standard model minus the Higgs boson, W boson, the Z boson, and top quark. So and the gauge symmetry is broken. That so the electroweak gauge symmetry is broken. Here there is a very dramatic transition. Yeah, degrees of freedom change. So I understand there were lectures last week about this effective theory. Then the only degrees of freedom that are left is electrons and photons, and then only photons. And so that you can say that you can describe this, yeah, as a change of the number of relativistic degrees of freedom. There is of course some asterisks, yeah, you have to put, yeah, that even at low energy, yeah, we have even if you go to a low energy, we have, for example, stable particles like protons or nuclei, yeah, so which can exist also as non-relativistic degrees of freedom in that. And the second asterisk is that there is also gravity. But gravity, from the point of view of effective field theory, doesn't pose any problem. So we just add, instead of SMEFT, we have GR SMEFT, and we add a graviton to that picture, and then so on. And you can, for example, then at the low energies, you have a low energy theory of gravity and light. Yeah. So from the effective field theory point of view, having an effective theory of gravity doesn't pose any fundamental problems. It's a perfectly well-defined effective theory, as long as you say that that there is some cutoff above which you have some ignorance. Okay, so the next so let me start, yeah, with just a quick overview of SMEFT, yeah, so that we can set the stage for the more phenomenological lectures in the in the remaining days. So what are the fields, yeah, that we have here? There is we have blue one, This will also define my notation. G mu A. Weak bosons. W mu A. Hypercharge bosons. B mu. Then quark doublets. Q. The up-type quark singlets. See? And down type, same thing. D bar C. But then I have lepton doublets. L and charged lepton singlets, E bar C, and finally cherry on the top, X boson H. So these are doublets, so they have up and down quarks here. This is also doublets. They have U bar. And just maybe it's a moment to also introduce a bit of notation. So I will be using for most of the time. I will be when I talk about fermions, I will be using two component notation. Yeah, is everybody familiar with that or not? So people are often used to more to Dirac notation. So if you have a Dirac fermion, yeah, it's a 4-component fermion. Let's say it's a Dirac. You can write it as a pair of as a pair of 2-component fermions, and the same is F bar, which is F gamma 0 will be FC F bar. So gamma mu is 0. 0. It's in an appropriate basis where these matrices are 1 sigma I and sigma bar is 1 minus sigma I. So in this 2-component notation, yeah, when I write kinetic terms, yeah, I write it in this form. And then I M FC F minus M C. And then if you want to translate quickly, if you don't like the 2-component notation, you can mentally always translate when you see a fermion without the C mark. You just say that this is left-handed fermion. Dirac, I'm denoting this with big FL. This when you see the 2-component fermion with C, this is the right-handed. This is a right-handed fermion. Right. Gamma. Right. And then if you this is mass term. This mixes right-handed. That is FR bar FL, and this is FL bar FR. Yeah. So I hope this will not pose too much problems. Yeah. But whenever you have chiral theories, yeah, it's much easier to work with 2-component notation, especially if you have operators, yeah, breaking a lepton and baryon symmetries, because otherwise writing them in the Dirac notation is a little bit of a yeah, we got to write it. Bar is just F star. It's a complex conjugate. Yeah? Yeah, so there is a little bit more to this notation than I'm writing. Yeah, there are also, so this two-component fermions, they have spinor indices. I don't think I will need it at any point. Yes, I will not introduce it because, yeah, I mean. Oh yeah, sorry. Yeah, yes, of course. Yeah. I mean, it's the same at this point. Yeah. Okay. So what I'm using here, yes. Yeah. If you wanna go into details, yeah, there is a holy scripture, yeah, of two-component notation. Yeah. This is this reference, Dreiner, Haber, Martin. So I will be using conventions from this reference, yeah, which like gives every possible formula for the manipulation of the spinors. So okay, so these spinors, they have a two-component index, and when I write it, yeah, the two-component indexes, the two-component indices are always contracted in a Lorentz invariant way. There's only one way you can do it. So there is a notation. The convention is that when you contract this in this, so this has an index, alpha, and this has an index alpha dot. Yes, I didn't want to do it, but yeah. And then this, they have implicitly also have one dotted and one undotted index. So this looks like that, alpha dot alpha and alpha dot. So when you have dotted indices, you always, when you contract them, you always go up. And when you have undotted indexes, when you contract them, you always go down. Yeah. So here it's the same. So this is undotted indices, they go down. And here there are dotted indices, they go up. Yeah. So I will not be writing these indices because I don't think this detail will be really needed for anything I will be talking about. The rules, yeah, are fixed, yeah, how you do it, yeah, and then they are defined, yeah, in this reference. Okay, so now, what is SMEFT? SMEFT is the way I think it was something I found. So SMEFT will be like the most general theory made of these fields, subject to three assumptions. The assumption one is that is the usual Poincare invariance, locality, unitarity. So in other words, we will work in the relativistic quantum field theory where all these rules, yeah, are hardwired. The second assumption is that there is a mass gap, so that other degrees of freedom are other degrees of freedom than those listed, than those of the standard model, are much heavier. Where much heavier, of course, is not completely well defined, but at least a TeV. Yeah, that there is at least like some there is some well-defined gap, yeah, between standard model degrees of freedom and the other degrees of freedoms. And of course, this assumption is a leap of faith. Yeah, we don't know if it's true. Okay, we know it's not true because we know that there is another degree of freedom. There is a spin-2 particle called the graviton, and in principle, we should always write an effective theory also with the graviton. But of course, yeah, when we do experiments in the lab, the graviton is coupled with a coupling that is suppressed by energy over M Planck, and there is in almost all situations, yeah, it doesn't affect. So it makes sense to take the limit of M Planck equals to infinity, and this decouples graviton, and we don't worry about it. There might be, of course, yeah, if you go to higher energies, yeah, that would change, yeah. But when we're at low energies and we don't care, we also don't know. Maybe there are other light degrees of freedom. Maybe there is axion. If there is axion, that can change some things that I'm talking about. You know, there's some things I will talk about is not true. So there is this leap of faith here. And yeah, there might be also some other degrees of freedom. Yeah, but I will be assuming that they are not. Yeah, so that will be working the framework where I assume there's no other degrees of freedom. And of course, yeah, if you ever come to me and you discover some other light degree of freedom, it will be trivial to add it. Yeah, it will just be a minor complication, but the rules will be the same. And the last assumption here is SU3 cross SU2 gauge invariance. And the meaning, yeah, of this, yeah, is a little bit more subtle. So in nature, we have what the massless particle we have in nature is photons and gluons, of course, up to the scale when they disappear. Yeah, but photons and gluons are massless. And we know that if we have massless particles and we write a relativistic quantum field theory, then we need to have a gauge invariance associated with them. So any theory that follows this rules, yeah, it will have to have a SU3 cross U1 electromagnetic gauge invariance. Here we ask for something stronger, that there is SU2 cross U1 gauge invariance, so corresponding to electroic. So all the interactions that we write down, they will have to respect this gauge invariance. And this is an assumption because there exists formulation, yeah, of effective field theory with this degree of freedom where this assumption is weaker and you only demand SU3 cross U1. So this is called heft. So we will not be doing heft in this lecture. So what is the difference? What is the physical difference between these two theories? So that is a little bit more subtle. So let me just sketch like some an argument here. Yeah. So yeah. Okay. Yeah. You're right. Yeah. That there's another when I was discussing this, assumption will be that there is no right-handed neutrino, light right-handed neutrino.
But in general, say interpret that experimental results. To have.
So that's, of course, that's what Liang we're doing. And I don't know, I mean, I think that the assumption that right-handed neutrino is heavy is very well motivated theoretically, yeah, because you can write the mass for the right-handed neutrino is singlet. There is no reason that it should be small. Of course, it's another leap of faith here. This second thing is that when you have a right-handed neutrino in nuclear beta decay, maybe I will comment on that. I mean, I wasn't planning to, but I can comment on that in the lecture 5. The effect of the right-handed neutrinos, they don't interfere with the standard model. So you're sensitive only quadratically. So you have very little sensitivity to quadratic, to right-handed neutrino couplings in nuclear beta decays, unlike for left-handed neutrino couplings. Yeah. And so focusing on the couplings to which you have a good sensitivity, yeah, I think it's also a good motivation, yeah, not to do it. Yeah. So, and yeah, so most people, when they do nuclear beta decay and new physics, they do it a la Liang, yeah, and there will be right-handed neutrinos, which introduces a lot of unnecessary complications and makes the picture a little bit fuzzy, in my opinion. But yeah, it's. I didn't understand.
Left-hand, right-handed doublet both.
There's no right-handed doublets, yeah. So I don't have a right-handed neutrino in my theory, yeah. And these are singlets, yeah, they are not treated as that. So just going back, so what is the meaning of this gauge invariance? Is so this gauge invariance gives you additional correlations, yeah, between the different interactions. So if you, for example, take an example of a simple operator h to the 6, yeah, it will give you contribution to the cubic gauge coupling. Sorry, when you write it in terms of the Higgs boson, so we write as, let's say, the unitary gauge this is the VEF, this is the Higgs boson field, that's the square root of 2. But yeah, you will write it something, you will get a correction to, and then you will get delta lambda 5 H5 and then delta lambda 6 H6. What will happen here, yeah, is that because you get all these couplings from a single operator, there will be correlation. If you know the cubic coupling, you know the quartic coupling. On the other hand, if you do Heft, in the Heft approach, there is no electroweak symmetry, there is only electromagnetic symmetry, and the Higgs is treated as a singlet. So all of this are independent operators. Yeah? There is no correlations. And then what does it mean physically? Let me just sketch you an argument. If you have actually, gauge symmetry is something that it's not a real symmetry, it's always a redundancy in the description. So you can always introduce, even in the Heft, you could introduce gauge symmetry, and you write it that square root 2h dagger a minus v. So you can replace the Higgs boson field with a square root of 2h dagger h minus v. So you can write even in the Heft, when you have all these couplings are independent, you can write it in a gauge invariant way. But of course, you're losing something here, which maybe I didn't spell it. You're introducing non-analytic couplings. And non-analytic couplings, so this is something that you get, and now maybe a leap of faith. This is something that you get when you integrate out particles that are massless or that have or whose mass vanishes in the limit of no electroweak symmetry break. So if you had your UV theory here contain the particles whose masses are proportional to the Higgs field, VEF, which you can have. Yeah, you can have a fourth generation, for example. Yeah, but there's more examples. You can construct examples like that in the 2 Higgs doublet models. Then you integrate out these particles. You will get what you will get is a effective theory that contains non-analytic or non-polynomial interactions in the low energy effective theory. So, for example, if you integrate out the fourth generation, chiral generation, yeah, of quarks, you will get that Lagrangian will contain something like that, h to the 4 log h dagger h, and non-analyticity is here, and that's the general fact. Yeah, whenever you you have no right to integrate out or when you integrate out a massless particle, you get something that is non-analytic, or in other words, non-local. So if you have this distinction between full gauge symmetry and limited gauge symmetry is actually very much related to the second assumption about the mass gap. Heft describes UV completions, is an effective theory for UV completions that are non-decoupling, of the non-decoupling type. It means that there is some particles, some degrees of freedom in the UV, whose mass would go to 0 if in the limit of no electric symmetry breaking. Yeah. I mean, you can. So then you in the unitary gauge, this would do nothing. But then if you go to introduce the Goldstone bosons, you will have this corresponds to some power series of that will go like G over V, where this is a Goldstone boson field, which is sort of a proxy for longitudinal degrees of freedom. And this is the V is Higgs-Webb. And that means that this theory secretly has a cutoff at lambda equals 4 pi V. So when you work with Heft secretly has a cutoff at the scale not far from electroweak symmetry breaking scale. And this is, you can understand, I mean, that usually the masses of particles, yeah, it will be given by some coupling times Webb of the Higgs. And this coupling cannot be arbitrarily large. It can be larger than 4 pi. So the new degrees of freedom, they have to appear below the scale of 4 pi V. So this is, of course, yeah, this is a little bit of storytelling. Yeah, I don't want to, if you're interested, yeah, I can give you the whole story later. Yeah, so it's actually, yeah, 4 pi V over log, yeah, of some coupling, yeah. It's true, yeah. Yeah, so, yeah, but you need the couplings, yeah, to be 10 to minus 10, yeah, to really make this, make a difference here, yeah, so practically it is. Okay, let me go forward a bit. Yeah, so as I said, if you want this to know a little bit more about this story difference between Heft and SMEFT, I'll be happy to discuss it in more detail after. So let's build the Lagrangian according to these rules. So we have the Lagrangian of SMEFT, yeah, is built in according to canonical dimensions. Yeah, so we write it each 2 plus Lagrangian equals 3, 4, 5, and so on. And the motivation of that is that so this D is a canonical dimension, yeah, of each term, and the motivation of that is that the amplitude, yeah, in this in this theory, yeah, will also have so, or rather, to write it more carefully. The term of dimension D will contain couplings, or in this context, the couplings are called Wilson coefficients. And because Lagrangian has to have a dimension 4, if you have a term, interaction term, yeah, with dimension D, this will have to have a dimension mass to the power of 4 minus D. Yeah, so for the dimension 4 interactions, the couplings are dimensionless, but if you go to higher dimensions, they will have dimensions of 1 over a mass. And then the amplitude will, the contribution to the amplitude will be e to the power of D minus 4. So if you write it instead of some scale lambda, so we assume that this Wilson coefficient will depend on some scale lambda, which is identified with the scale of new physics. Then this will be given by e to the lambda, the power of D minus 4. So the higher dimensions, the higher power of e over lambda, you're contributing to the amplitude. And in the EFT is valid by definition well below the scale lambda. So the higher dimensions, the less important this term will be for low energy phenomenology. Okay. So what do we have at dimension 0? At dimension 0, we have nothing. Yeah, we cannot construct from these fields. Maybe I should just say, yeah, that the gluon fields, they have dimension 1, or the bosonic fields, they have dimension 1. Fermionic fields, they have dimension 3/2. So we cannot construct anything at dimension 0. So far, so good. At dimension 1, similar story. If we had a singlet in the theory, we could write this linear tadpole term in the Lagrangian, but we don't have any singlets in the SMEFT, so nothing here. At dimension 2, we already have something. We can construct a single term. This is the Higgs field mass term. So you see that this counting here that I was doing quickly here is that the Wilson coefficient here has dimension 4 minus 2 equals 2, and I write it as mu squared. We know what this mu is. This mu is something like 80 GeV squared, 88 GeV squared, if I'm not mistaken. This is a little bit of a mystery. Yeah? So natural power counting would suggest that mu should be of the order of the cutoff scale lambda. Also, the loop corrections, you would expect they should drive this up to the lambda. And this is called hierarchy problem. Yeah? So in EFT or in SMEFT, we don't solve the hierarchy problem, but we have a very clear definition of what the hierarchy problem is. It's a breakdown of naive dimensional analysis, yeah, when we write the lowest dimensional term in the Lagrange. If you go to gravitational effective theories, yeah, then you have a similar problem. At dimension 0, you can write square root of minus g in that case. It's a dimension 0 term in the effective Lagrangian, and then its Wilson coefficient has dimension lambda to 4 minus 0 to lambda 4, and that's a cosmological constant. There is even more spectacular breakdown of dimension analysis there. We don't know, yeah, how big is this problem. Yeah, if the cutoff of SMEFT is 3 TeV, then we have a problem here, yeah, of the order, yeah, of 10 to minus 2. I mean, you would expect that this mass mu squared, yeah, should be lambda squared, maybe divided by some loop factor. Yeah. So, and then in that case, it's called little hierarchy problem. Yeah, but maybe cutoff of SMEFT is 10 to 16 or 10 to, yeah, we don't know. Could be 10 to 16 GeV. And then this is a big hierarchy problem, and this is the people have been thinking about this problem, yeah, for like, well, all my scientific life, yeah, and they haven't solved it. Or they come up with a lot of solutions that unfortunately don't seem to be realized in nature. So we will not be solving it, we'll just be stating this problem, and we go to dimension 3. At dimension 3, there is also nothing we can write in SMEFT. Again, this is not a law of that there is no dimension 3 terms in the Lagrangian. For example, if we had a right-handed Lagrangian, we could write a mass term. If we had a right-handed neutrino, we could write a Majorana mass term for right-handed neutrino, which has dimension 3, but we don't have a right-handed neutrino by assumption. And so we don't have anything at dimension 3. At dimension 4, it gets more interesting, yeah, because we have mu plus E sum of F left-handed sigma F plus R. Sorry, this F bar. Then we have d mu H dagger, d mu H, and then we have a Yukawa terms. Y, H, F, and then minus lambda. And then so these are the type of terms that we can write at dimension 4. And of course, this and this is just a standard model. Yeah, so these are at dimension 4, we have a renormalizable terms plus the Higgs mass term that would be the standard model. So this is the first success of the EFT paradigm, yeah, is that all of these terms have been seen in nature. We've seen the gauge kinetic terms, including the interaction terms that predict. We've seen interactions that follow between the fermions and gauge fields. These are very well tested, that follow from the fact that this d mu contains gauge bosons. We've seen the effects of this term, yeah, in particular, this produces the masses of W and Z bosons when Higgs gets VEF. We've seen most of the Yukawa terms, yeah, so maybe not all of them, but yeah, so we still don't have any evidence, yeah, for Yukawa terms, yeah, of the first generation fermions, but we've seen the Yukawa terms for the third generation fermions, and we've seen some terms, yeah, for the second generation. So we've seen the Higgs coupling to muon. For the quartic Higgs, yeah, we don't see it directly, yeah, but we've seen the effect, yeah, that the Higgs mass is proportional to the quartic Higgs term, so you can also see it. The only thing that we haven't seen this is the so-called theta-theta term, and that's another problem. Yeah, this is called the strong CP problem. So we can write at dimension 4, we can write this term, and the coefficients of this, I mean, in this normalization will be something less than 10 to minus 12. So there's one problem, but otherwise this works like a charm. Yeah, so everything that is predicted to exist, yeah, by just this dimensional, that at this dimension 4 or equals level exists in nature. So let's go to dimension 5.
We already have seen half of the spectrum of our theory. We come to this is we already have seen marginal operators of SATPP.
Yep, but wait for it, yeah. Now we go to dimension 5. At dimension 5, actually, the situation is a bit simpler. At dimension 5, we have the H, where this lambda H, this is a shortcut, yeah, for this kind of SU2 invariant contraction of two doublets. And at dimension 5 level, there's only one kind of operator that we can write. And then when Higgs gets a VEF, so we write X equals 0 equals 2. When Higgs gets a VEF, and this, then Higgs has a VEF at the lower, so it gives you, it marries with the upper, so this becomes C, C V squared over 2, and then mu. Sorry, so I don't know how to solve the problem that my nu and my v, they look the same, but this is nu and this is v. So when the Higgs gets a VEF, this produces Majorana masses for the neutrinos. And again, my neutrino masses has been seen. So the this MEF paradigm predicts, yeah, that you should first see effects, yeah, of relevant and marginal operators, and then the first deviation that you should see from that is should be from dimension 5 operators. And lo and behold, that's what happened. Yeah? This is called Weinberg operator, one of several things that is called a Weinberg operator. So Weinberg predicted it or wrote down this operator in the late 70s, yeah, and well before the discovery of the neutrino masses, yeah. So that was a fantastic prediction that is probably the strongest argument, yeah, for this EFT paradigm as applied to physics beyond the standard model, yeah, because that was indeed the first effect that we have seen of physics beyond the standard model. And so what does it mean now? Yeah, so we don't know. But also, when you turn around this argument, yeah, this is like the most natural way to understand neutrino masses. And so what is this? Yeah, so this higher dimensional operators, the role is to describe this, to describe these monsters and dragons that we don't know. So this is an effective description of some physics that happens at a very high scale. So okay, so the prediction, yeah, is that mass of the neutrinos is of the order of Wilson coefficient, which has dimension of 1 over mass, according to that counting, times v squared, where v is 246 GeV. So now, what kind of physics this can be? So it's very easy to write UV completions, yeah, that will give you this operator. For example, one possible UV completion, yeah, is you add something that Tuhin is rooting about, is you add right-handed neutrino to the theory. I will be denoting it. I will write it like that: LH N C plus 1/2 M N N C plus Hermitian conjugate. And then we can integrate, sorry, this is both. Yeah, so this is the Majorana mass for the right-handed neutrino. Now we can, if we integrate out the right-handed neutrino, at tree level integrating out is very easy because it's just, sorry, it should be plus or minus. So integrating out a field, a massive field at tree level is just solving the equations of motion. So the equation of motion for this will be that M and C is equal to YLH. So NC is equal to 1 over M YLH. And then we plug back the solution into the Lagrangian. So we get effective Lagrangian will contain. So if we plug it here, we'll get y squared over 2 m. We plug it here, we get the same, but with the other sign. So at the end of the day, this will give you us y squared over m LH LH, which is exactly this operator we started with. So we identify that C is equal to 1 over 2 y squared over m. Yeah? So this Wilson coefficient, it carries information about the masses and couplings of in the high energy theory. But of course, we don't know that this is the theory. Yeah, we now only see the low energy manifestation. We could have just as well, we could have a theory, we could write a different theory. So this is called type 1 seesaw. Another possibility is so-called type 3 seesaw, yeah, where we could write it y L L twiddle delta L plus mu H twiddle delta star H. So we could write this kind of interactions, yeah, of the of the mass. So delta would be a scalar. And this twiddle, this is LK is epsilon KL L star. Yeah, so you can make a doublet into a doublet of opposite hypercharge using this operation. So what did I write here? Okay. So now if you integrate out this, you will get that C is equal to, or maybe not equal, it's we're not calculating it, but you will get something like that. That is proportional to this Yukawa coupling times this trilinear coupling over mass squared. This is called type 3 seesaw. So this is a blessing and a curse, yeah, because a lot of different physics in the high scale reduces to the same operator at low energy. And this reduces to the same because there is only one. So whatever there is that gives a mass to the neutrino will give us this operator. So it's good from the low energy point of view that we can just have limited number of parameters that we describe our neutrino physics. But of course, this is a curse and a blessing. Yeah? The blessing is that we have a simple low energy description. The curse is that we cannot connect this EFT operator to a particular new physics models. Yeah, there is always a selection of models, yeah, that you can find. And now it's actually very easy to look at this, which models there are automated tools that give you all the models that give you particular operators. There is something that is called SOLD, written by people from, I don't know if they're probably not from Granada anymore, yeah, but originating from Granada. And you just write which operator and whether you want all possible models that give you this operator at tree level and all possible models that give you this operator at loop level. And the program, the Mathematica code, gives you the list of all possible models. So, right? What is this? I think it's called solved. So yeah, this is same company that does Matchmaker, yeah, but this is a simpler tool, yeah. Doesn't do, but it still gives you the. Yeah, so that's true. Yeah, that if you different models will give you. In this case, no, yeah, because at least at the dimension 5 you have only one, so there is not little you can do, and you would have to go to dimension 7, for example, or maybe some dimension. I don't think they produce any dimension 6 operators. So in this case, no, yeah, but of course, yeah, when you have that will give you the correlation. Okay, so I should finish in now. So I still have 15 minutes. Yeah. Yeah. Okay. So yeah. I'll just say that this is dimension 5. At dimension 6, all hell breaks loose. Yeah. So here we had a very nice situation that we had only one operator. So if you take into account that there is 3 generations of leptons, and then you count separately Hermitian conjugate, I think there is like 12 operators here. Here, okay, where did I write it? It should be on this. Here, it's for dimension 6, we have 84 independent operators for 1 generation, and wait for it, 3045 operators for regeneration. So this is the number of independent operators. Yeah, so things complicate a bit because of this rich flavor structure of the standard model. Yeah, so there is a lot of things to that will need to be constrained. So maybe first, by the way, so you probably know a different number, 2,499. That's the number that is usually being quoted, but that doesn't include the baryon number violating operators. If together with baryon number violating operators, you add another 500, yeah, and that's the final tally. Now the question is maybe we don't need to even think about it, yeah. So the scale of this operator. What is the scale of that is characteristic for dimension 5? If you take coupling of order 1, you will find that the scale of new physics is 10 to, I mean, the neutrino masses, you say that it's something like 0.1 eV. And so neutrino mass, yeah, is this operator times v squared, yeah, so you'll find that this has to be 1 over 10 to 15. So if the scale of new physics is 10 to 15, then most of these operators wouldn't matter for us. The only ones that would matter would be the ones that lead to proton decay. So in that scenario, yeah, everybody who does physics beyond the standard model should go home and start doing something different, except when you're doing proton decay, so working on hypercavalcande, on Dune, or when you're doing neutrino physics. It's a possibility, yeah? It's a perfectly well-defined hypothesis, yeah, that might be true. That the real expansion scale of SMEFT is 10 to 15 GeV, so there is little we need to worry at the dimension 6. However, this doesn't have to be true. So first, you see that this Wilson coefficient, yeah, this is coupling squared over mass. So it's possible that the coupling is not 1, but the coupling is small, and then this mass might be much smaller. That's one possibility. Second possibility is that the dimension 5 operators, or in general odd dimension operators, are special because they violate B minus L. So it's possible that physics that violates B minus L is very high, at high scale, but there is other physics, other new physics that doesn't violate B minus L and therefore doesn't produce dimension 5 operators. And that physics can be at much lower scale. So it still makes sense to study dimension 6 operators and look and try to find. So in this, you have a lot of different types of operators. Yes, so for example, you can make a dimension 6 operator by taking 6 Higgs fields. This is a funny dimension 6 operator. This does very little to most of physics, except that it's at tree level. It only the only effect that is observable in the near future is that it gives you the correction to the cubic Higgs, triple Higgs coupling. Yeah, so this is something that some holy grail that will be searched for, yeah, in the next phase of LHC and in the future colliders. So we will be interested in low energies. Yeah, so for us it will be not too interesting. Another way you can do dimension 6 operators, you take 4 Higgs fields, four Higgs fields and 2 derivatives. So you could so an example of this operator, yeah, is H dagger H box H dagger H, where box, yeah, is 2 derivatives, and this gives you corrections to the Higgs couplings. It actually gives you universal corrections to all the Higgs couplings to matter. Since I said I will not be talking about the Higgs bosons, this will be not of interest. This will be not of interest for us. But there is another operator of this type. So again, two derivatives for Higgs fields. And this gives you correction to the Z boson mass, and therefore it affects electroweak precision observables, and I will talk about it tomorrow. Another, you can take two Higgs fields and two field strengths of a gauge boson. That is example of these operators is just this, H dagger H, for example, G mu nu A, G mu nu A. So by the way, in my notation, I don't care writing mu nu up and down because there is no ambiguity. Yes, you can. I always write it as it's convenient. Yeah? So I don't use the Einstein notation here. Yeah? It's always implicitly contracted, yeah, with Minkowski eta tensor. So this gives you a correction to the Higgs coupling to gluons, to the Higgs production at the LHC. Again, not interesting for us, but will, for example, this operator is a different story. A B mu nu. When the Higgs gets VF, this will give you a mixing between the Z and gamma. And that is, again, something that affects electroweak precision observables. Yeah, so we'll talk about it tomorrow. You can take three field strengths, F mu nu cube. So for example, an operator I will talk about for a moment in the lecture 3 is this one. You can, and if you put a twiddle on that, so you take the dual tensor, this is called again Weinberg operator, and it gives you, this is a CP violating operator that contributes to the neutron electric dipole moment. So this is something that can be tested at low energies. Then next, you can take three Higgs fields and two fermions. Three, this gives you another three. And for example, H dagger H, bar H. See? And that gives you corrections to the Higgs coupling to electrons, or if you take another generation, muons or taus. Again, that's interesting for Higgs physics, not for low energies. An interesting class of operators is this. You take two Higgses, one derivative, and two fermions. Yeah. So, for example, you can take something like that. L bar, sigma L. That gives you. So this means H dagger d mu H minus d mu H dagger H. This notation with the arrow. When the Higgs gets a VF, this will give you correction to the Z coupling to two fermions. So this is something interesting for electroweak precision observation. Next class of operators, you can take H, F mu nu, and two fermions. For example, L bar, very similar to this operator where I'm writing here, L bar H, E bar C, and except that now, sorry, I put sigma bar mu nu bar C, and sigma bar mu nu is equal to sigma bar mu, sigma nu minus sigma bar mu, sigma mu I over 2. And this gives you corrections to the anomalous magnetic and electric moment of the electron. So that's interesting from a low energy point of view. This one, and well, there's one more page here somewhere. 2, 9. Yeah, and the last class of operators, which actually contains most of this 3,405, is 4 fermion operators. So yeah, there's many ways you can write 4 fermion operators. Like for example, you can take 2 leptons. No. And there's many different ways. Yeah, you can put them together, and then again there is a generation structure. So this 4 fermion operators, especially for those that contain the first generations, yeah, then they will be very relevant for various low energy precision observables. So I will talk about these 4 fermion operators a lot in the next lectures. And what do they have a very simple interpretation, yeah, because they correspond to some forces that you have forces, yeah, that have exist at higher scales, and then they get integrated out, yeah. So when you can have you can have 2 fermions, and then there is some massive force carrier that couples to these fermions, and then if it gets integrated out, you get a 4 fermion operator. So by the way, so those yeah, all of these operators, yeah, again you can get them. There are models, yeah, that you can write to obtain them. The interesting thing is that these operators that gives you this give you the dipole and moments. Those only arise at loop level. Yeah, they don't arise from renormalizable theories at tree level. And the same story is here with these operators, yeah, with 3-gauge fields. Yeah, they only arise at loop level. So this would arise, yeah, if you have you integrate out some heavy particles, yeah, that have a color charge, and yeah, this arise, yeah. For example, you can have some this would be leptons. You can have here in the loop. You can have some heavy vector-like leptons, yeah, that they will give you these operators, yeah. But you always need if you have a renormalizable UV completion, you always need a loop, yeah, to get these operators and other operators, yeah. And this is the same also for this. This also arise from loops, and the remaining ones, yeah, they appear at tree level. Okay, so it's a good moment to finish. So the overview, and tomorrow I will discuss electroweak precision observables, yeah, that corresponding to on-shell decays of Z and W bosons.